Programmable Magnetic Rotary Encoders by Austria Microsystems. Welcome to the training module on Austria Microsystems Programmable Magnetic Rotary Encoders. This training module introduces the magnetic rotary encoders for accurate angular measurement over a full turn of 360 degrees. Our outline consists of Hall effect rotary encoder basics, overview of AS504X Programmable Magnetic Rotary Encoder, and basic operations. Linear Hall sensors generate a DC output voltage proportional to the strength of an applied magnetic field and can be used for high-resolution angle sensors when placed near a diametrically magnetized magnet. The rotating magnet generates a sinusoidal waveform, 1 full wave per revolution. However, this type of setup can be used only for a limited angular range because the output voltage is ambiguous at angles greater than 90 degrees in both directions from the zero crossing point. In practice, only the quasi-linear range up to 45 degrees can be used for accurate angle measurements. This setup, being very sensitive to the position of the sensor relative to the magnet and to unwanted external magnetic fields, requires tight mechanical tolerances and in many cases magnetic shielding. Making angular measurements over a full revolution requires additional measures. Austria Microsystems' approach uses 4 Hall elements rather than 1 and spaces them equally underneath a diametrically magnetized rotating magnet to generate 4 sinusoidal waveforms, each phase shifted by 90 degrees from its neighbor, as shown in the equation. By using differential amplification of 2 opposite sensors, H1 minus H3 and H2 minus H4, is to generate 2 90 degrees phase-shifted signals with double amplitude. These 2 analog signals are digitized by ADCs and processed further in the digital domain. A codec, also known as Coordinate Rotation Digital Computer, transforms sine and cosine information into angle and magnitude information. The AS5040 is a contactless magnetic rotary encoder for accurate angular measurements over a full turn of 360 degrees. It is a system-on-chip combining integrated Hall elements, analog front-end, and digital signal processing in a single device. To measure the angle, only a simple 2-pole magnet rotating over the center of the chip is required. The magnet may be placed above or below the IC. The absolute angle measurement provides instant indication of the magnet's angular position. This digital data is available as a serial bit stream and as a PWM signal. The encoder's robustness and contactless measurement principle make them a suitable choice for applications where electromechanical, inductive, optical, or other measurement principles are either too unreliable or too expensive. The sensors can be used for contactless rotary position sensing and brushless DC motor commutation in different industrial applications. For automotive applications, they can be used to sense steering wheel position and gas pedal position, or to control headlight position and power seat position. They can also replace traditional optical encoders or potentiometers. Here's the block diagram of the AS504X encoder. The integrated Hall elements are placed around the center of the device and deliver a voltage representation of the magnetic field at the surface of the IC. The sigma-delta analog or digital conversions and a coordinate rotation digital computer provide the angle and the magnitude of the Hall ray signals. The DSP is also used to provide digital information at the outputs mag-INCN and mag-DECN that indicate movements of the used magnet towards or away from the device's surface. The AS504X senses the orientation of the magnetic field and calculates a binary code. This code can be accessed via a synchronous serial interface. In addition, an absolute angular representation is given by a pulse width modulated signal at PWM pin. The AS5040 has an interval 3.3 volt low dropout voltage regulator to allow the device to operate at either 3.3 volts or 5 volt supplies. In addition, the various incremental output modes can be selected by programming the OTP mode register bits in the AS5040. The AS5045 does not support these two functions. There are two important parameters, resolution and accuracy. These two are not necessarily related to each other. Resolution is the smallest angle step given as the number of uniformly continuous steps per revolution. Resolution is mainly determined by the resolution of the ADC and the calculation depth of the cordec. Accuracy is the deviation between the indicated angle and the actual angle. Several parameters affect the accuracy and eventually define the quality of an encoder, including phase error of Hall signals, matching error of Hall sensors and amplifiers, nonlinearity of the ADC, and nonlinearity due to misalignment of the magnet. The AS504X encoder series is using ADCs which have an excellent ADC linearity. These magnetic Hall sensors also use parallel signal processing, which keeps the phase error negligible even at high rotational speeds. The daisy chain mode allows connection of several AS504Xs in series, while still keeping just one digital input for data transfer. This mode is accomplished by connecting the data output to the data input of the subsequent device. An RC filter must be implemented between each PROG pin of device N and DO pin of device N+1 to prevent the encoders to enter the alignment mode in case of ESD discharge, long cables, not conform signal levels, or shape. Using the values R equals 100 ohms and C equals 1 nanofarad allow a maximum CLK frequency of 1 MHz on the whole chain. The serial data of all connected devices is read from the DO pin of the first device in the chain. The PROG pin of the last device in the chain should be connected to VSS. The length of the serial bit stream increases with every connected device. The AS504X provides a pulse width modulated output, whose duty cycle is proportional to the measured angle. The PWM frequency is internally trimmed to an accuracy of plus or minus 5%. An analog output may be generated by averaging the PWM signal using an external active or passive low-pass filter. The analog output voltage is proportional to the angle. 0 degrees equals 0 volts. 360 degrees equals VDD 5V. Using this method, the AS5040 can be used as a direct replacement of potentiometers. This figure shows an example of a simple passive low-pass filter to generate the analog output. R1 should be greater than or equal to 4.7 kiloohms to avoid loading of the PWM output. Larger values of Rx and Cx will provide better filtering and less ripple, but will also slow down the response time. After power on, programming the AS504X is enabled with the rising edge of CSN with PROG equal high and CLK equal low. 16-bit configuration data must be serial shifted into the OTP register via the PROG pin. The first CCW bit is followed by the zero position data and the mode setting bits. Data must be valid at the rising edge of CLK. After writing data into the OTP register, it can be permanently programmed by rising the PROG pin to the programming voltage VPROG. To exit the programming mode, the chip must be reset by power on reset. The program data is available after the next power up. The alignment mode simplifies centering the magnet over the chip to gain maximum accuracy and XY alignment tolerance. This electrical centering method allows a wider XY alignment tolerance than mechanical centering as it eliminates the displacement tolerance of the die within the IC package. Alignment mode can be enabled with the falling edge of CSN while PROG equals logic high. The data bits D9 through D0 of the SSI change to a 10-bit or 12-bit displacement amplitude output. A high value indicates large X or Y displacement, but also higher absolute magnetic field strength. The magnet is properly aligned when the difference between highest and lowest value over one full turn is at minimum. The alignment mode can be reset to normal operation mode by a power-on reset. Typically, the magnet should be 6 mm in diameter and greater than or equal to 2.5 mm in height. Magnetic materials such as rare earth samarium cobalt, neodymium iron boron, and alnico are recommended. The magnet's field strength perpendicular to the die surface should be verified using a Gauss meter. The magnetic field BV at a given distance along a concentric circle with a radius of 1.1 mm should be in the range from plus or minus 45 mt to S75 mt. The best linearity can be achieved by placing the center of the magnet exactly over the defined center of the IC package. The magnet may be placed below or above the device. The vertical distance should be chosen such that the magnetic field on the die surface is within the specified limits. The typical distance, Z, between the magnet and the package surface is 0.5 mm to 1.8 mm, with the recommended magnet size of 6 mm by 2.5 mm.